Today we're going to talk about series solution for differential equations. Well, most higher order linear differential equations with variable coefficients, they cannot be solved just using elementary functions. Many higher order linear differential equations with variable coefficients cannot be solved using elementary functions. That's where we use this series to solve those differential equations. So we are going back to elementary calculus and using series to solve those differential equations. For example, suppose I ask you to solve this differential equation. Example, solve y prime equals to y plus x squared, and suppose you have initial condition at 0, your y is equal to 1. So what are we going to do? We're going to use a series. Well, let us work with y equals to the sum Cn x to the n and start from 0 to infinity. As you can see, we have a power series with center at 0. So our center is going to be the same. Remember how we write this in expanded form. Y is equal to c sub 0, x to the 0 plus c sub 1, x to the first power, c sub 2, x squared plus the rest of the terms. What is the first derivative of this series? We need the first derivative of the series because we're going to substitute that into the equation here and solve it. Y prime is equal to, so the very first term is going to be 0, it's just a constant. The second term becomes c sub 1 plus, the third term is 2c sub 2x. If you continue this, you get 3c sub 3 x squared plus the rest of the terms. So now let's do the substitution. On the left-hand side, we're going to have c1 plus 2c2x plus c sub 3 x squared plus the rest of the terms. And on the right-hand side, you're going to have your y, which is equal to c sub 0 plus c1x plus c2x squared plus the rest of terms. And don't forget to write down the x squared. Excellent. Here. Now we are just using basic algebra. If you factor out x squared here, you're going to have c1 plus 2c2x plus 3c sub 3x squared plus the rest of the terms equals to c sub 0 plus c sub 1x plus x squared c sub 2 plus 1 plus the rest of the terms. Let's bring all terms to the other side. So here you have C sub 1, let me use a different color, minus C sub 0. And let us copy down 2C2x minus C1x. Plus, we're trying to look for a pattern here. 3C sub 3 x squared minus x squared C sub 2 plus 1. Plus the rest of the terms. And on the right-hand side, you're going to have 0. So let's see what's happening here. My constant is C1 minus C sub 0. And I have x to C2 minus C1. I have x squared 3C3 minus C2 minus 1 plus the rest of the terms equal to 0. Left-hand side is equal to right-hand side. So what's the meaning of that? It means that each coefficient must be 0. So C1 minus C sub 0 must be 0. 2C2 minus C1 must be 0. 3C sub 3 minus C2 minus 1 is equal to 0, and the rest of the terms. Can we find a pattern here? Well, as you can see, C1 and C sub 0 are equal to each other. From the second equation, C2 can be written as C1 divided by 2. But at the same time, C1 and C sub 0 are equal to each other. So C2 is C sub 0 divided by 2. Now here, C sub 3 can be written as C sub 2 plus 1 divided by 3, or C sub 0 divided by 2 plus 1. Let's just try to simplify the whole thing. C sub 0 divided by 2 plus 1 divided by 3. So C sub 3 becomes C sub 0 plus 2 divided by 3 times 2. Well, we are seeing a pattern here. I have C1, which is C sub 0. I have C2, which is C sub 0 divided by 2. 2 is just 2 factorial. C sub 3 becomes C sub 0 plus 2 divided by 3 factorial. You can continue this process. If you continue this process, you're going to see that C4 becomes C sub 0 plus 2 divided by 4 factorial, and the rest of them. Well, we can write our series this way. I'm going to go back to my series because this is the solution for this differential equation. So my y becomes, well, here I have C sub 0. Guys, note that your y at 0 is equal to 1. So if my x is just 0, my first term becomes 1. That's x equal to 0. C sub 0 is 1 and the same as C sub 1. So this is 1 plus 1 times x plus C sub 2 becomes 1 divided by 2 factorial x squared plus, we can continue this process. 3x to the third, 3 factorial, and the rest of the terms. As you can see, the behavior is very similar to an exponential function written in its analytic form.